The next graph neural network predictive model that we'll build will perform graph classification. Graph classification involves predicting properties of the graph as a whole, that is, making inferences about entire graphs or subgraphs. Graph classification problems use the features associated with nodes and edges and the connections in the graph in order to make predictions about the graph itself. In the hands-on demo that we are going to look at shortly, we'll use graph classification to predict whether a certain protein molecule is an enzyme or not. How does graph classification work? Now, every node in the graph that you have in your input dataset is likely to have features, and it's also possible that the connections that you have between the nodes of your graph also have features associated with them. You can then use the node features and edge features aggregated together in a meaningful way to generate an embedding representation for the graph as a whole. And you can use that embedding representation for classification. You can take that embedding representation, pass it through a linear classifier, and use that to categorize the entire graph. In this visualization that you see here for each graph structure, we generate an embedding representation in latent space, and it's this latent space representation that is used for classification. Let's talk about how we'll actually generate an embedding representation for the entire graph. Now, all graphs may have node-level properties or edge-level properties or both. Now you perform regular graph convolution on any other transformation and aggregation operation in order to get embeddings representations for these properties, all of the node-level properties and the edge-level properties. The embeddings generated for node properties and edge properties will include the local neighborhood information, the local neighborhood around each target node or each edge. Now we want a single embedding representation for the entire graph. And the way you obtain that is by gathering these embeddings across all nodes or edges of the graph, and then using pooling layers to aggregate this information for the graph. Pooling layers perform some kind of aggregation operation. It can be summing, averaging, or any other, but aggregating across all of the embedding representations of the individual components of the graph will give you one embedding representation for the graph as a whole. And it's these aggregated embeddings that you'll use for classification. When you feed in a large amount of data into a neural network model for training, you typically feed this data in batches, and you can perform mini batching of graphs as well using PyTorch Geometric. Model training tends to be more stable and robust when you feed in data in batches, and we'll apply the same idea to graph neural networks as well. In our graph classification problem, we have a number of graphs categorized into different classes or categories, and we want to feed in these graphs during the training of a model in a batched form. But how do you batch graphs? PyTorch Geometric stacks the individual graph adjacency matrices in a diagonal fashion, and it sets up a very large graph with multiple isolated subgraphs. Here in the visualization, we have two graphs G1 and G2. The node features of the graph are represented by X, and the adjacency matrix is A, so we have X1, X2, and A1, a 2 for the two graphs. Now, in order to stack these graphs together in a single batch, you take the adjacency matrices A1 and A2 and stack them in a diagonal fashion, as you see here on screen. Since G1 and G2 are separate graphs, none of the nodes in graph G1 will be connected to nodes in graph G2 and vice versa. So the off-diagonal of the stacked adjacency matrix will contain all zeros. The stacked adjacency matrix thus represents a large graph with multiple isolated subgraphs. The node features for the individual nodes in the different graphs are concatenated in the node dimension, so they're concatenated as you visualize here on screen. And this mini batch data is what is fed into the neural network model to compute updated embeddings for every node across all graphs. In graph classification models, you can use regular graph convolution networks to generate embeddings for each node, which are then aggregated together to get an embedding representation for the graph as a whole. Here's the mathematical formulation that we've been looking at throughout this course. These are the node embeddings at layer L+1 for every node V in our graph structure. If you look closely at this mathematical formula, observe that we perform normalization across the embeddings of the neighboring nodes. Now, this neighborhood normalization might work well for node classification. However, in some cases, it's possible that neighborhood normalization decreases the expressivity of graph neural networks in distinguishing certain graph structures. So certain nuances of how graphs are connected together might be lost because of neighborhood normalization. An alternative formulation for the graph convolution layer has been proposed in order to improve graph classification tasks. This alternative formulation skips the normalization step, thus maintains the raw information from the neighbors. This helps preserve more detailed structural information in your graphs. In addition, this alternative formulation adds a skip connection to the graph neural network layer to preserve central node information. This skip connection is a direct connection from the input features of the node to the output of the GN layer. This helps in retaining the target node's original information while still allowing the network to learn from its neighbors. When we do our graph classification demo, we'll use the graph convolution layer with neighborhood normalization, as well as a GNN layer that does not include neighborhood normalization and uses this alternative formulation. And we'll see whether eliminating neighborhood normalization improves our classification task's performance.